In this class, we will show you how to use digital certificates, private keys, the SSL and TLS protocols, and content inspection with secure protocols. Here's an overview of what we will discuss. We'll explain elements of symmetric and asymmetric cryptography, the SSL and TLS protocols, certificate-based user authentication, and how cryptography impacts content inspection such as antivirus and DLP scans. After completing this class, you should have these practical skills. You should be able to upload certificates, private keys, and CRLs where appropriate. You should also be able to configure FortiGate and browsers to use certificates and keys for SSH, SSL, or TLS content inspection, and to troubleshoot misconfigurations. Secure traffic protects your communications between you and someone else. There are 4 properties: data privacy, data integrity, authentication, non-repudiation. Not all secure channels will require all 4 features. For example, technically, the RFC for IPsec VPN allows tunnels to be built with no encryption. But because people almost always want privacy for important data, and it's usually pointless to make data private if you don't know who sent it, and that it hasn't been tampered with, in practice, most secure traffic has at least the first 3 properties. Data privacy is achieved with encryption. Encryption applies a pattern to the information that effectively makes it unintelligible to a third party before it travels across the network. Only the intended recipient, who also knows the pattern, is able to decrypt the data and access the information. There are several ciphers in common use, such as Triple DES and AES-256. The strength of a cipher varies by how difficult it is for attackers to break. Note that when we say traffic is secure, we usually mean that it uses strong encryption. But you should never forget that the strongest of encryption can be defeated by allowing unscanned, unencrypted USB key drives to be carried from the office. This has happened in government and military environments, so physical security is first. But you can't physically secure everything. It's not practical, and it's not even theoretically possible. So once you've physically secured as much as you can, how do you protect data while traveling over your network? What if your data must travel through a possibly hostile network, such as the Internet? Encryption is also crucial. Encryption is strong if, computationally, it's very difficult for unintended recipients to decode. This is often because there exists no known mathematical or other method to break the code other than through sheer brute force, trial and error. So while in the classic cryptography example, Bob and Alice might use ROT13 that simply replaces the letters with others in a different position in the alphabet, this isn't very good encryption. It's very fast for a computer or even a human to analyze that pattern and decrypt it. What affects how strong the encryption is? We'll discuss that in detail later. If your data is private, but it's been corrupted in transit or falsified, then effectively your traffic isn't secure either. How do we guarantee that the message has arrived intact? There are a few methods to verify data integrity, and they don't require repeating the entire message to the sender, which would be very slow. Again, mathematics has been extremely useful. These are algorithms where a much smaller number, such as a checksum, is mathematically related to its larger chunk of data. If the short checksum is as expected, then the corresponding and usually much larger message is guaranteed to be as expected. Important information shouldn't be trusted unless you can verify the identity of the person or device who sent the message. so authentication's role is also important. There are stronger ways to authenticate than simple usernames and passwords, which were implemented near the dawn of computing. We'll see some stronger authentication later. Finally, and related to authentication, is non-repudiation. This means that the sender cannot claim later that she or he did not transmit that data. The sender's identity is somehow bound to the message. So, interrelatedly, data integrity is important. You want to ensure that the non-repudiation data hasn't been forged or that the non-repudiation would be very weak. Let's return now to encryption. How can we make data private? People have invented many solutions to this over thousands of years. Several methods involve using a piece of data called a key to mathematically scramble the message in a way that only the recipient can predict and undo. But keys aren't always the same on both the sender and recipient side. Here we show the mechanics of symmetric cryptography where the key is the same on both sides. One side begins with the plain text data to be sent. Both sides agree upon an algorithm and share the same key before sending the message between them. The plain text data is processed using a mathematical calculation that uses an algorithm with a key and plain text data as inputs to generate the encrypted data, which is then sent to the recipient. The receiver then reverses the algorithm using the same pre-shared key to obtain the original unencrypted data. So, with symmetric cryptography, the same key is used to encrypt and decrypt the data. This is something that must be shared between both sides beforehand and in a secure fashion. The result is that it does not scale well. The more connections there are, the more pre-shared keys are usually needed. It is possible to reuse the keys with multiple connections, but if one of them is compromised, all messages using that key are compromised. Encryption and decryption with a symmetric key, however, is faster for encrypting large amounts of data. Let's see now asymmetric cryptography. It is a technique that uses not a single key, but a pair of keys, a public key and a private key. Both keys are mathematically related. They are generated from the same random number and using the same key generator algorithm. However, because of the algorithm, large prime numbers are popular since these are impossible to factor and very difficult and rare to find. It is extremely difficult to get the private key from the public key. In the other way too, it is practically impossible to guess the public key from the private key. What is encrypted with a private key can only be decrypted with the public key. In a similar way, what is encrypted with the public key can only be decrypted with the private key. Public keys are distributed publicly. Private keys are never distributed and must be kept secret by the owners. The public keys are made available by using different methods. Those methods include email, secure websites, or public repositories such as a public key infrastructure server such as a CA. Private keys, on the other hand, and as I said, must be stored in a secure and private place, such as a file in a single physically secure location with very restrictive permissions. Let's see with this example how asymmetric cryptography works. Data is still encrypted using a key, but the key that the sender is going to use is the public key of the recipient. Everyone has that key. The encrypted data is then transmitted to the recipient. As the data was encrypted with the recipient's public key, it can only be decrypted with the recipient's private key, which only the recipient has. So even though everyone has the recipient's public key, Still, only the recipient will be able to decrypt the data. In comparison with symmetric keys, once a shared key is available to everyone, the connection is compromised. How are these encryption algorithms applied? How can they also be used to strengthen authentication? A digital certificate is a digital credential that identifies someone or something. That someone or something can be either a network user or a network service. The certificate contains information about the entity that it is identifying, including the entity's public key. A digital certificate is issued and signed by a certificate authority, or CA, which certifies that the digital certificate and its content is trustable and valid. Digital certificates can be classified into three groups. A CA certificate identifies a CA. It contains the CA's public key that is needed to decrypt the signature in the local service and user certificates. A local service certificate identifies a network service, such as an SSH server or HTTPS website. A user certificate identifies a network user. User and local service certificates are also called end entity certificates. As I said, the certificate includes information about the entity, but it also contains information about the CA that signed the certificate. These are the most important fields that any certificate has. There is a serial number that is unique to each certificate signed by the same CA. In the case of a user certificate, the subject contains the user's login name. In the case of a local service certificate, the subject contains either the fully qualified domain name or the IP address of the server. The signature of the CA is encrypted using the CA's private key. The issuer field is the name of the CA that signed the certificate. The valid from and valid to fields specify when the certificate is valid, including the expiration date. This slide shows how user authentication works with digital certificates. When the user is authenticating, it sends its digital certificate, which includes not only its public key, but also the signature of the CA that certifies the certificate. The signature is encrypted with the private key of the CA. The authentication server must trust the CA. In other words, it must have the CA certificate of the CA that has signed the user certificate. That CA certificate contains the CA's private key, so the authentication server will use the CA's private key to decrypt and validate the signature in the user certificate. Additionally, for a user certificate to be valid, it cannot be listed as untrustworthy in a certificate revocation list. We will talk about these lists later. Finally, the user certificate must be within its validity period, so it has not expired yet. If any of these verifications failed, the user authentication would fail. Let's see the case now of a user connecting to a web server. An HTTPS server identifies itself by using a digital local service certificate. When a user is connecting to the website, the browser receives the website's local service certificate. In this case, it is signed by a CA called CA1, and the signature is encrypted using CA1's private key. The user's browser must trust the CA. In other words, it must have the CA certificate of CA1 installed, which contains CA1's public key. This public key is used to decrypt and validate the signature in the website's local certificate. The most common browsers already have pre-installed the CA certificates of the well-known public CAs. So installing the CA certificate in the browser is usually not required as long as the website certificate has been signed by a well-known CA. However, It is a required step if the certificate has been signed, for example, by a private CA. The browser also verifies that the certificate is still valid, in other words, that it has not expired yet. Additionally, the certificate must not be listed in any certificate revocation list. If any of these verification fails, the browser will give a certificate warning to the user indicating that something is not right with the site being visited. SSL is the cryptographic protocol used by the HTTPS protocol and by other standard protocols such as SMTPS and FTPS. So when a user is connecting to an HTTPS site, this is the protocol used between the web server and the browser to authenticate and encrypt the data. Let's take a look with more details at an SSL communication that takes place with FortiGate when a user's browser is accessing the GUI via HTTPS. What I'm going to show applies not only to HTTPS access to the FortiGate GUI, but also to HTTPS access to any website. You enter the URL of FortiGate into your browser. The browser sends an HTTP hello packet to the web server, which in this case is FortiGate. The server receives the hello and sends back its certificate. The certificate, as we already know, contains the public key of the server. This key will be used by the browser to start encrypting the data. The browser then evaluates the certificate for validity. Does it trust the CA that signed the certificate? Is the certificate still valid? Has the certificate been revoked? The browser creates a symmetric key. This symmetric key, or secret, is encrypted using the server's public key. The encrypted symmetric key is then sent to the server. The server uses its own private key to decrypt the encrypted symmetric key. Finally, both sides use the symmetric key to encrypt the user and web server data. So, in an SSL session, asymmetric cryptography is used to generate and share a symmetric key. After that, symmetric cryptography is used to encrypt the user and server data. The symmetric key is valid only for the length of the session. If you close the current session, that symmetric key is no longer valid and cannot be used again. When a new SSL session is created, a new symmetric key will be created between the browser and the server. So, how do we get signed a digital certificate for our FortiGate device or web server? The most common way of doing this is by generating the private and the public key first. Usually, those two keys are generated internally by the device where the certificate is going to be installed. After that, we submit the public key to a public certificate authority such as GoDaddy or VeriSign. The CA verifies first that the information submitted is valid. After that, the CA generates and signs a digital certificate which contains the public key sent by the user. The CA will also encrypt the certificate and its signature using its private key. Let's see with more details how this works. As I said, the network device generates the private and public keys. The public key is stored in a file with the standard format PKCS10. The file contains what is called a Certificate Signing Request, or CSR. The CSR also contains information about the network device and the user, such as IP address or fully qualified domain name, and company name. What we submit to the CA is the PKCS10 file with the CSR on it. After the CSR is submitted, and while waiting for the signed certificate, FortiGate will show the certificate as pending. This slide shows how we generate the CSR from a FortiGate device. When we click on Generate, we must fill out the CSR form. After that, as I said, the status of the certificate will be pending. The administrator can now download the PKCS10 file and submit it to a CA. When the administrator receives the signed certificate back from the CA, it must import it to the FortiGate. After that, the status of the certificate will change from pending to OK, meaning that we can start using it. If you wish to have the FortiGate unit preventing certain certificates from being used, then you will need to maintain a certificate revocation list, or CRL. A CRL contains the serial numbers of all the digital certificates that cannot be trusted anymore. For example, digital certificates of an ex-employee that left the company can be added to the list. When FortiGate is validating a certificate, it will check that its serial number is not listed in a CRL. CRLs must be kept up to date manually by the administrator. We import CRLs under Certificates, CRL in the FortiGate GUI. Digital certificates stored in a FortiGate device can be backed up to a PKCS12 file. The file will include the keys, private and public, and the certificates themselves. The backup and restore can be done only from the CLI and requires the use of a TFTP server. Once this information is backed up, we can restore it back to the same FortiGate device. We can also restore it to any other FortiGate regardless of the model or firmware version. A backup of the FortiGate configuration also contains the keys and certificates. However, in the case of a configuration backup, the restore can only be done to a FortiGate unit of the same model and running the same firmware version. Some FortiGate devices offer a mechanism to inspect and apply protection profiles over SSL encrypted traffic. It is called SSL content inspection. Under normal circumstances, without SSL content inspection, encrypted traffic cannot be inspected as the firewall does not have the key that is required to decrypt the data. Let's see how this mechanism works. FortiGate is located in the middle of the communication between the user's browser and the website, example.com. The website has and knows its private key. When the browser connects to the site, the web server sends its certificate, which contains its public key. Its certificate has been issued to example.com by a well-known public CA. FortiGate intercepts the web server certificate and generates a new one on the fly. The new certificate is also issued to example.com, but this time it is issued by a CA called FortiGate CA, which is not a public CA. The FortiGate also generates on the fly a new pair of public and private keys. The new certificate contains the public key generated by FortiGate. So, now, the FortiGate unit will use the FortiGate public key, not the web server's public key, to start the encryption. The FortiGate can inspect the traffic now, as it has the equivalent private key. The FortiGate on the other side will use the web server's public key to start the encryption and establish the conversation with the site. It is important to mention that SSL inspection is not available on all FortiGates, but is only supported in some models. So, as we have seen, SSL inspection requires an SSL proxy certificate that allows the unit to generate a new pair of keys and a new certificate. The unit must do it on the fly and each time the user is connecting to a different site. In other words, the unit must act as a sub-CA. So the certificate that is required for SSL inspection is not a usual one, but one that has either the CA field equal to true or the key usage equals to key cert sign. An administrator cannot get this kind of certificate from a public CA. they must be generated privately. The FortiGate models that support SSL inspection come from factory with one SSL proxy certificate that can be used for SSL inspection. It is called Fortinet CA SSL Proxy and is signed by a CA called FortiGate CA. When doing SSL inspection, your browser will start displaying a certificate warning each time a user is connecting to an HTTPS site. The reason for this warning is that the certificates received by the browser are now being signed by the FortiGate, which is a CA that the browsers do not trust. There are basically two ways for avoiding these warnings. The first option is to download the FortiGate CA root certificate from the FortiGate and install it in all the workstations. FortiGate CA is the CA that is now signing the certificates. So by having its CA root certificate installed, browsers will start trusting it. Another option is to generate a new SSL proxy certificate from a private CA. In that case, we need to install this new certificate into FortiGate, configure the unit to use it for SSL inspection, and install the root CA certificate of the private CA in all the workstations. Many customers complain about these certificate warnings and about the time it could take to remove them from all the workstations. However, it is important to understand that this is not a limitation in FortiGates, but a consequence of how digital certificates were designed to work. The only way for a FortiGate device, or for any other vendor device, to inspect encrypted traffic is to intercept the certificate coming from the server and generate a new one. In other words, the unit must do a man-in-the-middle inspection. SSL and digital certificates have been designed to give a warning each time a device is doing man-in-the-middle inspection. We are going to use the FortiGate factory default certificate for SSL inspection. This slide explains briefly how to download the Fortinet CA root certificate and install it in the browser. We must go first to Certificates, Local Certificates, select the certificate Fortinet CA SSL Proxy, and click on Download. We are going to get a CSR file, which we can open it to check its contents. From there, we will click on Install Certificate to start the certificate installation wizard. In the wizard, we must select Place all certificates in the following store. Then, we must click on the Browse button and select the Trusted Root Certification Authority folder. On the FortiGate side, enabling SSL inspection is quite simple. First, we need to create a SSL SSH inspection profile. Here, we can specify which SSL proxy certificate is going to be used for SSL inspection. The drop-down list will only show the certificates that can be used for SSL inspection. The profile must then be selected in the firewall policy. So all of the security profiles in the policy, web filtering, anti-spam, antivirus, etc., will be applied not only to unencrypted traffic, but also to the encrypted traffic selected in the SSL SSH profile. Finally, let's see how to configure a FortiGate device for certificate-based user authentication. Users with a digital certificate are called PKI users. Initially, the FortiGate's GUI will not show the option to create those users. It is a configuration section that is initially hidden from the GUI menu. You must create your first user from the CLI using the commands shown in this slide. When creating the user, you must specify the CA that has signed the user certificate and what the user certificate's subject field must contain to be valid. After the first user has been created from the CLI, you can now access the PKI user section in the GUI to create new users or edit existing ones. For each PKI user, you can also enable two-factor authentication, which means that the user will need not only to present a valid certificate, but also to type a valid password. Now it's time for the labs. In this lab, you'll generate a certificate signing request from a FortiGate device. In a second exercise, you will enable SSL inspection.